Good afternoon, class. Today, I could have sworn I silenced that thing. What? Oh, I turned off the Wi-Fi. Forgot to silence it. Oh. Turned off that little blue light filter. Also, forgot to turn off the volume though. But anyway, today we're looking at inverse functions. So give me a moment. I think I'm going to move this thing way over here to be out of the way. And I need to do some writing. So let me come over here and let me move that down there. Recall one of the fundamental concepts in this class. A function has no repeated x values. I'm going to do some writing and then we'll look through and do some the first 5 or so examples in the homework. But right now I'm just going to write stuff. A function has no repeated x values. A function that is said to be one-to-one has no repeated y values. And it's hyphenated one-to-one function. So if it's a one-to-one function, in addition to having no repeated x values, it has no repeated y values. So here's an example of a one-to-one function. F equals, I'm just going to write it out with ordered pairs. Remember we had 3 different ways of expressing functions: ordered pairs, algebraic expressions, and graphs. I'm going to start off the first one just by looking at an ordered pair. Let's say 0, 7, 4, 0, and 3, -1. That's an example of a one-to-one function. Notice every x value is different and every y value. Now, you say we'll use a 0 for x and use it for a y here. That's fine. You just can't have 0 repeated as a y value. You can't have 0 repeated as an x value. This is an example of a one-to-one function.
And it's also a recall though, right?
Pardon me?
Because you're saying function has no repeated x values. Is that another one, or is it all just...
It's a type of function. Not all functions are one-to-one. Any function that has repeated y values is just a function. But this has no, the x values are different and the y values are different. And I think I'm going to make a note. This is ordered pairs. I said that there were 3 ways that we use to express functions. One of them is just looking at ordered pairs. And so we can look at an ordered pair and determine if the function's one-to-one. Every y value is different. What about this one? I'm going to make another one. I'm going to call it G. Is that one-to-one? No. The y values of 14. You have 14 here and 14 right there. So this G example is not one-to-one. Another method of expressing functions, the one that we use most frequently, are algebraic expressions, or maybe algebraic equations. Algebraic equations. What could appear in an equation that would make something not be one-to-one? What could your equation have that would make you repeat y coordinates, not 1 to 1? Okay, you're right, a positive and a negative, but in that event, it wouldn't even be a function, okay? So how about, let's see, what are those things that cause all those problems? Maybe even exponents. Think about x squares. X squares take, but it doesn't matter whether the number is positive or negative. When you square it, what sort of a number do you get? Okay, let's just, I'll let y'all think about that for a moment. We said ordered pairs, algebraic. How about this third one? Let's look at a graph. Let's look at this graph. Let's see. Here's the graph I'm going to look at. Remember, with the function, to determine if a graph is a function, we'd use the vertical line test. Does it pass through the graph, or does a vertical line pass through the graph more than once? And so this is clearly a function. It's a parabola, correct? So let's look here. Give me this x coordinate would be a positive number. This point where the graph is passing through the x-axis. Do you agree the x coordinate is positive? What's the y value? Are we moving up or down? 0, okay. What about this point? We're moving to the left. That means negative, but the y value is still 0. We have repeated y values. So this thing is not 1 to 1. Okay, and what equation appears, what appears in the graph of a parabola? What variable expression must appear in the graph of a parabola? How about an x square? X squares, the even exponents, take whether it's positive or negative. Let's look at this right here. There's something called the horizontal line test. If you can draw a horizontal line so it hits the graph in 2 spots, then the graph is not 1 to 1. Here we already had a horizontal line, the x-axis. But if the graph didn't pass through the x-axis, if you can draw a horizontal line and it hits the graph twice, it is not 1 to 1. That's called the horizontal line test. And I think y'all are missing the point I'm trying to make about the things not being 1 to 1. Whether you're plugging in a positive x value or a negative x value, when you raise it to an even exponent, you expect to get a positive result. So, I say x squared, but even if your equation had an x to the 4th or any even exponent, then you don't expect the graph or the function to be 1 to 1. And that will be significant later. Any questions there?
It can't share itself.
I couldn't hear you.
It can't share itself.
I'm not sure I understand your question. That statement.
Like x squared, it can't share the same number.
Well, if it were x squared and whether you pulled in a positive 3, plugged in a positive 3 or a negative 3 for x, what are you going to get there? When you take negative 3 squared or positive 3 squared, what are you going to get? You're going to get the same y value, which is a positive 9. That's the problem with even exponents. I remember something else we were doing this semester. I remember working with another type of function. It didn't matter what happened on the inside. Once you performed this function, I remember drawing graphs of them. Sort of looked like this, but it was a V. What was it? No, not ovals. Not circles. The V, what did the equation with those V's have? whether it was positive or negative on the inside when you took the absolute value. The absolute value. I think I just answered it for myself. If you're looking at an absolute value function, it cannot be 1-to-1. So the things that makes up an equation not be 1-to-1, for the most part, it's even exponents. If you see even exponents in your equation, you expect it not to be 1-to-1. And absolute values. If you see absolute values in your equation, you don't expect the graph to be 1-to-1. And remember what an absolute value looked like. Wasn't it a V? So it would fail that horizontal line test. You could easily draw a horizontal line so that it hits the graph in 2 spots. And let's see. Okay. I'm going to make some other examples. I'm going to go back to this ordered pair idea for the time being. Well, before I go on, I think we'll do some problems here. The homework's going to start off very painless. This is one of those. I thought we had it set up so that you had to at least click the videos before you could go to the assignments. Sometimes we remembered to click that button, and apparently sometimes we forgot, okay? Well, let's just get started here. The first few are going to, if you understand what I've been saying, these first few questions are going to go pretty painlessly.
Yes.
Is this function 1-to-1? Yes. It doesn't matter where you draw that horizontal line. Are you going to hit the graph in 2 or more spots? No. All slanted lines are 1-to-1. Maybe that's something we want to write down. I think it's significant, even if you all don't. I'll say note. All slanted lines are 1-to-1. So, better go back and answer that question. We said, yes, this is 1-to-1. Y'all agree? No horizontal line's going to hit it twice. And what about this one? It's hard to tell, but this thing is not, for a second it looks like it's going to turn around and start going back down, but they don't show that it's turning around. So you're to assume, you can't make the assumption it's going to turn around. You got to assume that it's just going to keep on going like that, increasing slowly. So will a horizontal line hit it twice? I don't think a horizontal line is going to hit that thing twice. Yes, this is also 1-to-1. I was expecting it to be no, but let's see. Hold on, then I'm going to make this thing bigger. Okay. There. Oh, maybe I should get rid of that. No. There. Okay, and I said yes, it is 1-to-1. Okay, number 3. Oh, well, wait a minute. I need to discuss. I'm going to do some more stuff before we write that, or we discuss that. I want to make up some examples. I'm going to have 2 functions. F is the function with the ordered pairs 0, 4, 1, 5, and 2, 7. Then I'm going to skip a line here. The function g is, let's say, -3, +9, +3, +9, and 2, 4. Let's make a note. Is F 1-to-1? Yes, it is. It is 1-to-1. Is 1-to-1. What about G? Is it 1-to-1? No, it's not 1-to-1. G is a function. It's just not 1-to-1. get rid of that pen. The inverse of a function is formed by just swapping the x and y coordinates. To denote the inverse of a function, we have a special notation. It looks like I'm saying f to the negative 1 power, but that is not an exponent. Raising a function to an exponent is meaningless. What that's saying is, hold on. I forgot, right? I can make this writing a little bigger for the time being. Right there. That's just saying the set of ordered pairs that f to the negative 1 power is read as the inverse of f, and it's formed by reversing the ordered pairs. 0, 4 becomes 4, 0. 1, 5 becomes 5, 1. 2, 7 becomes 7, 2. All we're doing is just swapping. That's what an inverse means. You're just swapping the x and y values. G inverse. Now, do you agree? G, it's not 1 to 1, but it is a function. Notice, every x value is different. So G is a function. It's just not 1 to 1. Reverse the ordered pairs. Negative 3, 9 becomes 9, negative 3. 3, 9 becomes 9, 3. And what's this last ordered pair going to be? 4, 2. I think we have a big problem. G was a function, but it wasn't 1 to 1. When we form the inverse, do we still have a function? No, right there. We have repeated x values. The repeated y values were in the original function, and it's okay to have repeated y values. It's still a function. But when you swapped the ordered pairs, you picked up repeated x values. So as a result, G inverse is not a function. The only reason we discuss one-to-one functions now is because only one-to-one functions have inverses that are functions. Yes, we can still form the inverse, but the thing that we're going to get is not a function. And in general, if the function isn't 1 to 1, we're not going to want to find the inverse, okay? So I'm going to say this is an important note. Only 1 to 1 functions have inverses that are functions. But to form an inverse, all you're doing is swapping the x and y values. And when we start working with algebraic equations and start trying to find the inverse, we're going to remember all you do is swap the x and y to form an inverse. So with that in mind, let's come back over here. Go on to number 3. Decide whether the given functions are inverses. I think this is something we can do. You probably don't even need to try to write it down. Okay, here's x and f of x. So x, y. Here's x, y on the supposed inverse. Are they inverses? 5, negative 3. Yeah, that became negative 3, 5. 4, 5. Is it reversed? Yes. Negative 3, 2. And 2, negative 3. Yeah, they're reversed. Negative 5, 6. Reverses to 6, negative 5. So what do we conclude? Are these inverses? Yes, they're inverses. Any questions on our logic there? We're just looking and seeing if the ordered pairs are being reversed. Are these functions inverses? -2, -6, is that reversed? Yes. 0, 3, and 3, 0, yeah. I was expecting some no's along the way, but what do y'all think? Are these functions inverses? Yes, the ordered pairs are just reversed. So, yes. Yeah. Okay. If the following defines a one-to-one function, find its inverse. If it's not one-to-one, just select not one-to-one. This is a nice little multiple choice option, so you're not going to have to type in all those ordered pairs. First question, is this one-to-one? What do we look at to decide if it's one-to-one? Okay, there's no repeated y values. Every y is different. So yes, it is one-to-one. So we need to find the inverse. -12, 13 should become? It's A. Let's see. 13, -12. 2, -19. -19, 2. Yeah. -18 and 7. Becomes 7 and -18. I agree. Any questions on our logic? Okay. Well, they can't stay this short or this quick, or else we're going to get through early today. Okay. If the function defines a one-to-one function, find its inverse. If not, write not one-to-one. It's not one-to-one. I'm going to write this one down, okay? Just for the sake, I want you to have this in your notes. Here's the function. I've got to give it a name. I'm going to name it f. And there. Okay. We look and we see what number causes the problem. What? The 8. That 8 is being repeated there and there. Repeated y value. So not one-to-one.
So not one-to-one and cannot be inverse.
Right. Well, you could find the inverse. I remember using an algebra book once where, okay, it's not one-to-one. You can still find the inverse, but the inverse isn't a function. In most algebra books, they only want to find inverses that are functions, and that's what they want here. But you can find an inverse. It's just not going to be a function. Any questions before we go on? Oh, here's another one. It's another one that should go pretty quickly if you understand what I've been saying. Which one? B. Is it one-to-one? 3, 6, 2, -9. Yeah, it's one-to-one. See, I'll say it's B.
Yeah.
6, 3 became 3, 6. I agree. 36 became 630. Fine. Yep, I agree. Any questions there? Well, this is going to have to slow down at some point. Okay. Let's come over here. Let's look at... I'm going to make up an example. Let's say 4, 3. Is that one-to-one? Is this example I just made up 1 to 1? What do y'all think? Yes. Notice there's no repeated y values, so this is 1 to 1. Let's find the inverse. 4, 3 becomes 3, 4. Negative 5, 9 becomes 9, negative 5. 1, 2 becomes 2, 1. And 3, 1 becomes 1, 3. Since f was a 1-to-1 function, that means f inverse is a 1-to-1 function. Okay, let's see if y'all remember the terminology. What numbers are in the domain of f? The domain of f. Pardon? The domain is the x value, and we're looking at f, not f inverse. What numbers are in the domain of f?
4, negative 5, 1, and 3.
I agree. 4, negative 5, 1, and 3. Those numbers were x's in the original function. What do they become in the new function? Those x values become what?
9, 2, and 1.
Okay, wait a minute. What does 4, negative 5, what happens to 4, negative 5, 1, and 3? Where do you see them in the new function? Through the y's, that's the range. So the domain of the original function is equal to the range of f inverse. And that should make sense. The x's in the original become y's in the new function. The x's in the original become y's in the new function. Now let's apply that same logic to the range of f. We're looking at the range of f. What numbers are in the range of the original function? Okay. The range of f. The y's in the original. What do those y values become in the new function? The domain, the x values. The original y's become x values in the new function, just like the original x's become y values in the new function. So the range of f is equal to the domain of f inverse. Any questions on our logic there? Okay. The domain of f is equal to the blank of f inverse. What's going to go in this blank? The domain of f is equal to the range of f inverse. They have a little pull down menu and you select range. The range of f, the y's in the original, are equal to the domain of f inverse. Oh. I love it when they put in a little nice word and then they say it as convolutedly as they possibly can, just to, to make sure that teachers like us get to keep our job so that we're not completely outsourced by the computer. I like this last sentence. Note that f inverse is a set of ordered pairs yx, where y belongs to the domain and x belongs to the range of f inverse. Why don't they just say that x's and y's were swapped? Oh, goodness. Okay. Let me write this problem down. If you understand what they're asking for, it's very fast. If a function f has an inverse and f of negative 3 is equal to 6, then f inverse of 6 is equal to blank. Okay. there's the blank. Okay. Yes, okay. I'm going to pull a MyLab and I'm going to say it very convolutedly, okay? Let's write this statement here, this original statement, using an ordered pair. Remember the number inside the parentheses, that's x. So, when x is negative 3, what's the y value in the ordered pair? When x is negative 3, the y value is 6. So when we form the inverse, we swap those numbers. So the new x value becomes 6, and the y value becomes negative 3. So, if negative 3, 6 is the ordered pair in F, 6, negative 3 has to be the ordered pair in the inverse. Any questions on our logic? I think the problem here is just trying to make sure you realize that the y values in the original function become the x values, the things in the parentheses, when you're looking at the inverse. Any questions there?
I'm waiting to see why it's so easy, but it's going to get hard.
This is a pretty painless section. Now that I'm thinking about it, it's not too bad. If the functions are inverses of each other, input of the function is the output of its inverse, and the output of the function is the input of its inverse. I love it. Now they're using that old terminology. In the 90s, they decided that the reason people do bad in math was because it just wasn't any, it wasn't something they saw as being used in the real world. So they decided that from now on, instead of using the word domain, they'd call it inputs. And then the range, they would call outputs. And the books would have these little function machines. And written there by the little machine would be the equation. And the x would drop into the little machine, and it would drop out as a y. I said that was ridiculous. There's no function machines in this world. There are no function machines out there. So here we are telling them, you see, this is what you use it in the real world. You use the function machines in the real world. No, you don't. There are no function machines. But anyway, I like the way they've gone in there and they're using that same old terminology from the 90s. Okay. Let me see if I can find another.
That's why I flunked algebra in the 90s. That's why I flunked algebra in the 90s.
Oh, that was one of their little great innovations that wasn't that great. Oh. Let's see. Can you hear me now?
Oh, yeah.
Yes, okay. Oh, let's see. It's going to have to get longer than this eventually, right? Okay, and now it's time. Well, they're going to, first of all, I'm going to write the formal definition of inverse function. We know what an inverse does. We know it reverses the x and y coordinates. We know that. But we need an algebraic definition of inverse function. Let's assume that we have two one-to-one functions, f and g. Assume f and g are one-to-one functions. F and g are inverses if each of the following is true. two conditions. The first one, f composed with g of x. Y'all remember fog and golf? F composed with g of x reduces to x for every x in the domain of g. So if you find the composition and everything cancels out except for x, and number two, if you reverse the order, g composed with f of x reduces to x for every x in the domain of f. If you can perform the composition in both directions and you always end up where you started, that means the ordered pairs have to be just reversed. And to illustrate, I'm going to use one of those little mapping illustrations that we used in when we were discussing functions the first time. Let's say 1, 2, 3, 4. Let's suppose that f takes 1 to 3 and 2 to 4. If these functions are inverses, then the inverse g has to take 3 back to 1, and 4 has to go back to 2. This definition is saying that if you perform the functions consecutively in either order, you'll always end up where you started if the functions are inverses. So if we start at 4, let's perform the functions consecutively. G takes 4 to 2, f takes 2 back to 4. You're ending where you started. The only way that's always going to happen is if the ordered pairs are just reversed. These are inverses. Say you start at 1. 1 goes to 3, 3 goes back to 1. The only way that's happening is if the ordered pairs are just reversed. Suppose we had...
That's just because of the arrow.
The mapping that I'm showing that f goes from 1 to 3 and 2 to 4, and then g goes 4 to 2 and 3 to 1. Let's look at this one. 1, 2, 3, 4. And once again, this is abstract thought. This is not inputs and outputs of some little function machine. Let's suppose f takes 1 to 3 and 2 to 4. So f is still doing the same thing. Suppose g doesn't reverse the ordered pairs. Let's suppose g takes 3 to 2 and 4 goes to 1. So the red function is g, the blue function is f. If we perform the two functions consecutively, 4 goes to 1. Where does 1 go? 1 goes to 3. You're not ending where you started. So these things are not functions. This notation here, this composition is saying that you will always end up at whatever x value you started off with. So, but this one, not inverses. But we knew that these were not inverses based on our intuitive knowledge of inverses. We know that inverses have to have ordered pairs that are reversed. So if you have two equations, if they give you two functions and they tell you to decide if they're inverses, find their compositions. If both of them reduce to x, then they are inverses. And we saw some problems like that. We saw some problems in the not the last one, the assignment before this one. Do you remember we were looking at composition? I'm going to close that off, leave. Where is it? Y'all remember doing, let me find it. Let's see, here it is. I think we were doing this 1 week ago. 1 week ago we were, do y'all remember these last two problems? Oh, yes.
It's like an overview.
It was trying to get you ready for that definition. Remember, it gave us two functions, f and g. We found f composed with g of x and g composed with f of x. They both reduced to x. And then they asked, are they equal? And the thing was yes. And we're just trying to get you used to this idea that two functions that are inverses will have compositions that reduce to x in both directions. Do y'all remember that? I think there was oh, no, that wasn't it. Was it 11? I think there were two of them. Yeah, there were two of them.
I haven't done the homework yet on that, but I've done the videos.
Okay, so then you're going to, okay, so you're going to get there. How's your daughter doing?
Excellent.
Oh, that's great to hear.
Yeah.
So,
That's why I wasn't here. She had a couple complications.
but no complications now? Okay, that's what we want to hear. Okay, going back to this assignment. Question number 10. Determine whether the two given functions are inverses of each other. If you have two functions, and you're trying to decide, are they inverses? And I should say two functions written as equations. If they were just ordered pairs, we know how to decide if they're inverses. Just look and see if the x's and y's are being swapped. But if we have two functions that are written as equations, are they inverses? Well, I don't know. Let's find their compositions. Let me write them down. This is number 10. Are f and g inverses? So f of x is 6 over x minus 9, and g of x
6 over x plus 9.
6 over x plus 9. Yes, okay. Okay. Are f and g inverses? We're going to have to find the compositions. Find f composed with g. Find fog x. If it reduces to x, then we find goth x. If goth x reduces to x, then they are inverses. Now, if we find f composed with g and everything doesn't cancel out except for an x, we can stop the problem. They're not inverses. But just because we know one of the compositions is reduces to x doesn't necessarily mean the other one does. So we have to find both of them. Here we go. First of all, f composed with g of x. F is on the outside, and on the inside we have g of x. F is on the outside. This stuff here, 6 over x plus 9, is on the inside. So that says go to F. It's going to get messy. I hate to say this. We're going to replace that little blue x with this 6 over x plus 9. So we have 6 over. We're replacing that x with the stuff in the parentheses. 6 over x plus 9. What else do we have there in the bottom? Minus 9. We took, I remember what my brother would do. He'd circle the g of x. He'd take the g of x and plug it into f. We took the g of x, we plugged it in to f. So in place of that x, we had the 6 over x plus 9. Now, if they're going to be functions, everything should cancel out except for what? The x. I think something's about to disappear. What is it?
6 over 6.
No, the 9 minus 9 is going to cancel. The 9 minus 9 cancels, but be careful. We have a 6 over, and we have that small fraction, 6 over x. This is called a compound fraction, a fraction that contains additional fractions. That blue bar there, that's the major fraction bar. What I do to simplify compound fractions is I multiply above and below by the minor denominator. The minor denominator is the denominator of the fraction that appears within the big fraction. So the minor denominator is x. I'm going to multiply above and below by x. So 6 times x, that's just 6x. Something nice is about to happen here in the denominator. Okay, look at that. That's like an x over 1, isn't it? Remember cross-canceling? That's in the numerator. That's in the denominator. You can cancel the x's. Any questions on my logic there? So what's the only thing we have left in the denominator? No. The 6. I think Mary May's jumping ahead, okay? Because then you cancel the 6's and it leaves us with x. As I'm writing this up here, it's just crystal clear and so neat in my mind, but occasionally I look over there and I just jump. Oh my God, does it really look that messy? And I look back and, I see it all differently now. This is a mess. That looks like a mess. Any questions there? So I'm thinking they probably are. If this were a test and I were running out of time, if one composition reduced to x, I'd go ahead and say, yes, they are inverses and go on. But we have plenty of time. So let's go in the other direction now. G composed with f of x. That's saying we're going to take f of x and plug it into G. So G is on the outside, and on the inside we had f of x. That's 6 over x minus 9. So we're going to go to G, and wherever we see a variable, we're going to replace it with what? We're coming up here to G, where we got 6 over x minus 9. So right there, we're going to replace that little x with 6. We're replacing that denominator x with the blue 6 over x minus 9. And I still have something stuck on there. What is it? That plus 9. Realize it's not part of the fraction. Here's the major fraction bar. The major fraction bar is the fraction bar there in G. And we stuck in that little fraction down here. Here's the minor fraction. What's the minor denominator? Okay, multiply above and below by x minus 9. Resist the urge to distribute that 6 over x minus 9. Remember, we want to cancel. We want to cancel out everything except for what? X. And if you want to cancel, you don't want to start distributing. So I'd leave that 6 times the x minus 9 as it is, but look what I can do. Cancel that x minus 9. So we have... Feel free to move around.
You don't put the x minus 9 where the 9 is either?
No, you don't. It's up above and below the fraction. That 9 there has no part of the fraction. It's just an integer setting off to the side. Did y'all understand your question? We do not multiply. We're not trying to distribute an x minus 9 throughout. We're multiplying the fraction above and below. And do y'all see how this x minus 9 cancels here? Yes? So we have that 6 times x minus 9. We have that blue 6 left over. And what else do we have? Plus 9. If you distributed that 6 there, you couldn't do what I'm about to do. To cancel above and below a fraction bar, the thing has to be in a factored form, written as a product. Since we didn't distribute that 6, it's a product, we can cancel the 6. And we then get the x minus 9, and we still have that plus 9, which reduces to just x. So now we can say with 100% confidence, the composition reduced to x in both directions. So are these functions inverses? Yes. F and G are inverses.
And how come you didn't distribute the 6 with the x minus 9?
Okay, let's suppose that you had. Right here, you distributed the 6. That would have been a 6x minus. 6 times x is 6x. 6 times minus 9 is a minus 54 all over 6. And you still have that plus 9. You can't just cancel 6 because that 6 is, this thing is not written as a product anymore. It's written as a difference. What we could do is we could say we have two options to cancel fractions. Either we get it in factored form, or we split it up. 6x over 6 minus 54 over 6 plus 9. What's 54 divided by 6? So we have a minus 9 plus 9. What's happening?
Yeah, it's getting rid of the stuff.
Yeah, you definitely saved it.
So why did I not distribute that 6? Because otherwise I'd have to go back through and get it in factored form or split it up. One or the other. Uh-oh. Well, that's fun. What just happened?
Hey,
Ah, there it is. Oh. Okay. Oh, I bet we just got timed out. Let's see. What do we conclude? F and G are inverses. Any questions there? If we're given two functions, we can determine if they're inverses by finding their composition. If it reduces to x in both directions, great, the functions are inverses. If it does not reduce to x in both directions, then the functions are not inverses. Any questions? So the natural question at this point, okay, how do you find an inverse? Suppose you're given a one-to-one function. How do you find a formula for its inverse?
6 over x.
Is that the same problem as what we just did?
I was just looking at that to see if that actually works. Because if you put that plus 9 with the x, so 6 over x plus 9 equals 6
I guess that
over
plus
x
9.
minus 9.
Okay, that plus 9 there. Let me see. Come back. That's a 6 over x plus 9. So it's a minus. So you're saying we would make that a minus 9 there. Is that what you're thinking? No? Okay. Let's write out a sequence of steps. It's easy enough to find the inverse of a one-to-one function. To find F inverse, the first thing you need to do is convince yourself that the function is one-to-one. You don't have to go through algebraically and show that it's one-to-one, but you need to convince yourself you're working with a one-to-one function. I'll say verify that f is 1-to-1. Something that I talked about at the very beginning of the class today is finally becoming important. What do you want to not have in your equations if the function's going to be 1-to-1? Let's see, where is that? Algebraic equations, the ones that aren't 1-to-1. Remember I said that even exponents, x squared, x to the fourth, were absolute values. I think we can look at this problem we're about to do and convince ourselves. Is that 1-to-1? Yes. If that weren't an x, if that weren't x squared, would it be 1-to-1? No, it doesn't matter if you put in a positive 1 or a negative 1, you're going to get the same y value. But I see there are no no even exponents, there are no absolute values. So yes, this function is 1-to-1. And I'll write that down in a moment because I want to go ahead and state this little recipe for finding. We verify that f is 1-to-1, and I'm going to make a little note here in parentheses. I'll say no even exponents, I'll just write ABS value, no absolute value. Then the second step, tell me in words, what does an inverse do? What does an inverse do? Think about it. Switches the x's and y's. Okay. I think I'll say swap. Swap x and y. Everywhere you have an x, you're going to write a y. Everywhere you have a y, you're going to write an x. At this point, you have an equation that's a form of an inverse, but they're going to want it in inverse function notation. So the third step, you'll have to solve for y. And then step number 4, which is totally optional because they'll be typing the little F inverse notation for you when they're asking you to type in the inverse. We'll replace y with F inverse of x. Okay. So let's go back to that number 11. Okay, here's number 11. I want us to find the inverse for f of x is equal to 6 over x plus 9. I want us to find f inverse. And we've already said, yes, it's not 1-to-1. Although, it is 1-to-1. If there were an x squared or an x to the fourth, forget it. It's not 1-to-1. But there were no even exponents, no absolute values. So, yeah, I can convince myself that it's 1-to-1.
Maybe you should write that.
Okay, I'm going to write it out. The step number 1, f is 1-to-1. Because there are no even exponents in x, in f.
And no absolute values.
There are no even exponents or absolute values. Okay. Number 2, they want us to swap x and y. Wait a minute, I don't even see a y in this original problem. What's taking the place of y? No, there's some algebraic expression taking the place of y. That's the x value, f of x. This is just a fancy way of saying y.
I was going to say it.
That's just a fancy way of saying, that's right. This is y here. So we're going to swap x and y, so the y becomes an x. So this is second step. The y, that messy y that I have there, becomes an x, and the x becomes a y. Third step, we want to solve for y. We need the equation in the form y equals, we need that y right there by itself. So I'll put a little step number 3, and it's the solving for y that's the longest part, and even then it isn't that long. I'd get rid of that fraction. What could I do to both sides so we don't have a fraction, so we cancel out that denominator? Okay, so we're going to multiply both sides by that denominator, y plus 9. Oh, be careful. Can y'all read that? That's a y plus 9 times x. The right-hand side is going to work. Once again, this is so messy. Okay. The right-hand side is going to work out very nicely. What's going to cancel? Y plus 9, leaving us just a 6. But on the left side, we have a monomial times a binomial. We're going to have to distribute. X times y times x is xy, so xy plus, what else did you say? 9 times x is 9x. Did y'all follow? Any questions? That's the tricky step here in this problem. We multiply by both sides by the denominator. We cancel the denominators. The denominator y plus 9. We have to distribute here. It's x times y plus 9. We're trying to solve for y. There's only one sensible next step.
That's a fine way to do it, but you're going to get fractions sooner. What I would do if you're trying to get the y by itself,
I'd move that 9x. Now realize this answer is going to look different from the way the inverse did in number 10. In number 10, they wrote the two functions. One of them was a fraction plus an integer. I prefer my function in inverse to be written as a single fraction. And that's the form that I'm going to use, okay? I'm going to move the 9x to the right. So I have xy equals 6 minus 9x. And then it's x times y. What will I do?
now say it.
Mary May, now what am I going to do? Now it's where you say, starts with a D. No.
Divide. Divide a moment ago.
Divide by x. So the x's cancel. And we have y equals x all over x. Oh, wait, let me move it up.
So by the number 2, what is that?
Y plus 9. I'm multiplying both sides by y plus 9. And I ran out of room. You're right.
But you would leave the fraction on the other side, but do something to the other.
This fraction here is canceling out, but there's no denominator here to cancel out the y plus.
Like number 3, step 3, where you have xy divided by x, and then you have 6 minus 9x divided by xy. There's nothing happening on that side, but it is on the other side.
Well, this thing isn't factored. It's not factored, so you can't cancel anything. Let's first of all make a note that I said that once you solve for y, you've got your inverse. Here's the inverse that you can type in, okay? But step number 4, replace y with f inverse of x. So we replace y with the f inverse of x notation, but it's the step on the right side that's the answer. That's what you type in.
Oh, you wanted to cancel something here?
I'm going to go back to that. I'm going to go back to that. But this is the preferred form for the inverse. Okay. Well, that doesn't look like the step that they had on number 10. Sure it is. We can say, okay, split up over the minus. We have a 6 over x minus 9x over x.
And that's what you do if you want to cancel something.
If you want to cancel there, you then have 6 over x minus 9. Look at that number 11. The function f of x was 6 over x plus 9. And the inverse became 6 over x minus 9. Go back to, this is a bizarre coincidence. And this is just a coincidence that those numbers are so similar. It's just a coincidence that number 10, I'm sure, I want to leave. You see, it's a x minus 9, and the sign there was a plus. So 6 over x plus 9, but ours over here.
And then I said the inverse would be 6 over x minus 9 because of the, I guess, coincidence that those numbers just happen to be this.
No, the inverse should have been, if you were going to try to make a pattern, the signs are opposite. So I said it should have been a 6 over x. Since it was a plus in number 11, that should be a minus, and that's what we got. If you look, if you want to reduce it like that. But a fraction plus or minus an integer, I find that to be an undesirable form for a function. I will be writing it as a single fraction.
But nothing wrong with writing it like this if you want. But if you you start off with one
My problem is
fraction.
that people start canceling too
Yeah.
soon, okay? And that's what happens. People start canceling too soon. Here, the only
just
thing
say
that's
can't
canceling
cancel.
is that x. You can't cancel because there's not an x over there. Can't get it factored. Leave it as a single fraction. But if you type in for number 11, if you type 6 over x minus 9, they're going to count it right. That's just not the form that I prefer, and it's not how I'm going to type in the answer. What's going on? It's not wanting to do.
Go back to question 11.
Oh, you're on 10.
Oh, I'm still on number 10, all right. Okay.
No, that's-
So now we click there. We have a fraction. 6 minus 9x is on top. And on the bottom we have an x. Let's do another one.
Okay.
Well, you're right. Let's look back here.
Look back at your work. Any questions?
I verified that it's 1 to 1. I multiplied both sides by that denominator to get rid of the fraction. I'm trying to solve for y, so I get the thing that doesn't have a y on the other side, and then I divide by whatever y is being multiplied by.
So basically ignore number 4 though.
Well,
No, I mean, not really.
I
I
just
mean,
like-
you don't have to.
Because
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 it
did you see the
said-
way they have it when you were typing it
I don't
in?
remember anything.
It already
Okay.
had f inverse equals.
Look, they already had the f inverse of x. That's why I boxed it in right here. As soon as you get y by itself, the thing on the other side is what you're going to be typing into that box for the inverse function.
So do you need to write out step 4? No.
No. Well, you don't need to write out step 1 either, but you made me write it out.
Yeah,
Tony.
you're right.
Okay, number 12. Number 12.
Oh, I remember semesters when students say it's not 1 to 1 because of the exponent.
I didn't say there
I
was
had
anything
nothing
wrong.
students.
I didn't say there was anything wrong with the exponents. What did I say was the even exponents? Okay. We want to find.
So yes, that's a function.
It is a 1 to 1 function. Did
Yes,
y'all hear
because
that?
It's cubed and not squared.
Yes.
Okay.
Write
That
that
thing
out.
right there, that is an odd number. 3 is odd, so 1 to 1.
Oh, okay.
It's when you have even exponents.
Right.
If it had been an x squared minus 4x plus 7, or an x to the 4th minus x cubed plus 3x squared, it's the even exponents that make it not be 1 to 1. This thing is a one-to-one function. So f is 1 to 1. So now, okay, wait a minute. But you said that, so you're saying f of x is just a fancy way of saying which variable? That's y. So we're going to replace the y with not the x cubed, just the x. Then the x becomes a y, so you have a y cubed minus 8. Did y'all hear what Mary Mae was saying? She was making a classic mistake. You're only swapping, something, maybe when you're writing the problem down, maybe we should stop using this f of x notation. Just write it as y equals x cubed minus 8. And then the y becomes an x, the x becomes a y. The cube stays where it is, unfortunately. We have to solve for y. Well, first of all, any questions on how we're swapping there? F of x became an x, the x became a y, we still had a cube, and that minus 8 stuck there on the right-hand side. We're trying to solve for y. That's what I would do. I'd add 8. I'd get that y cubed by itself to give me an x plus 8. What do we do to undo a cube? We just need y by itself. We're going to have to do something to both sides. What are we going to do? Not square root, but cube root. We're going to cube root both sides.
That's what you were thinking.
And then you see what we're doing? We're using inverse functions. The inverse of the cubing function is the cube root function, and the inverse of the squaring function is the square root expression, but it wouldn't be 1 to 1. But technically, the inverse of squaring is the square root. You perform them consecutively; they cancel each other out. Those things cancel each other out, and you're left with just y equals the cube root of x plus 8. I'm feeling lazy, so I'm not going to replace y with that f inverse notation. I'm just going to box in that expression right there.
Right? It really was. The answer, would you... Okay, so the x is already...
I'm not sure.
So, go back to your notebook really quick.
Okay.
And see how you have your box.
Okay.
You leave the y by itself. So is it just...
Well, I'll wait to check.
Wait. Let's see.
Is it just that? So you ignore
because they're already... My math lab is typing in f inverse of x equals for you. The only thing you type in the box is the expression on the other side. Looking here at my math lab, notice they have the f inverse of x notation already written for you. You just put in the stuff on the other side. The cube root of x plus 8. Did y'all see how he was punching in? Is that the first time?
Maybe that's the first time we typed cube roots.
No, I don't think so.
Oh, it isn't? So you click on this thing there. That's the nth root button. Use it for anything other than square roots. You type in the index 3, and then down here.
I'm sorry.
Any questions there? I think. Oh, radius of a circle. Okay, so
12 was it. Starts with 13 is review and circle.
Any questions over inverse functions? Any questions on inverse functions?
Once we started working with functions, we never leave them until the last assignment.
Yeah, the last assignment, there are no
I remember
functions.
something from years and years ago mentioning to a graduate advisor, there was one teacher, I don't know if you meet her, Ms. Ritter. She didn't have her students write inverse functions. They just had to write the equation. Now I remember asking, I was tutoring students then, I asked my graduate advisor, why doesn't she make them solve for y and get a function? And she said, in the old textbooks, this teacher was really old, they didn't write it. It wasn't so crazy about functions.
Just like now it's crazy for interval notation.
And
okay, so we're getting through early today.
oh wow.